Welcome everybody for this instance of the Spatial ML seminar series. I'm happy today to welcome Endri Taka, who's going to give us a very interesting talk that he presented at ISFPGA 3 weeks ago about adding tensor slices in FPGA fabric that support sparse computation, which is a very interesting topic. So Endri received his Bachelor of Science in Computer Engineering from the National Technical University of Athens in 2019. And he's currently a PhD student at the University of Texas at Austin. And he's focusing mainly on novel hardware architectures for deep learning, specifically focusing on reconfigurable computing and FPGAs. He's also now a research intern at AMD working on optimizing dense matrix computations and GEM workloads on the Ryzen AI MPUs. So Endri, thanks a lot for making the time to give this talk, and the floor is yours.
Sure. Yeah, thanks, Andrew, for the introduction. Yes, so today I'll present my work called Systolic Sparse Tensor Slices, which are FPGA building blocks for sparse and dense AI acceleration. So basically, sparsity is an inherent attribute in modern deep learning workloads. It's classified in two major categories, structured and unstructured or random sparsity. However, typically, most current deep learning accelerators do support structured sparsity just because it's more hardware friendly than random sparsity. Notable examples are the NVIDIA and AMD GPUs and the Versal AI ML and Ryzen AI NPUs, which today support 2 out of 4 structured sparsity. So FPGA architectures have been optimized for AI, but typically they target, as of today, dense deep learning workloads. And some examples are the Intel Altera tensor blocks from industry or the tensor slices from academia. And now the research question becomes of how to architect AI-optimized FPGAs to target sparse deep learning workloads, which are the most of today's deep learning workloads, basically. So to this end, we propose the systolic sparse tensor slices, which target both sparse and dense DL workloads. SST slices employ a 2D systolic data flow for maximization of data reuse, and because these 2D systolic data flow are highly scalable. SST slices basically support the most common sparsity levels with the lowest possible area overhead. So we support 2 out of 4, which is 50% sparsity, 1 out of 4 with 75% sparsity. And we also introduced a new pattern that prior researchers have missed. It's the 1 out of 3 pattern, which basically leads to around 67% of sparsity. And what is interesting is that it basically fills the gap between the 50% and 75%. And note that, typically higher than 75% sparsity is not that common, just because it leads to very high accuracy degradation in most deep learning workloads, and lower than 50%, nobody seems to care that much, because 50% is where you typically consider a tensor to be sparse. We employ dedicated interconnects column-wise, which lead to significant FPGA routing savings. And we also support int8 and bfloat16 precisions. So our sparse SST-based general matrix multiplication accelerators attain up to 5x higher frequency and 11x lower area compared to traditional FPGAs. And our evaluation of state-of-the-art BITs and CNNs when using the SST slices shows up to 3.5x speed up with only a 13% area increase when we compare to dense in fabric FPGA blocks. So a little bit of background in the structure sparsity. Basically, what structure sparsity is, it imposes constraints on the sparsity patterns. So as you can see in this figure, we have a 2 out of 4 sparsity, which means we have 50% sparsity, where there are 2 non-zero values every 4 consecutive elements. And similarly, for 1 out of 4, we have 1 non-zero every 4 elements, and 1 out of 3, we have 1 non-zero every 3 consecutive elements. So now we don't want to store those zeros, so we keep the matrices or tensors in a compressed representation format, where we store only the non-zero values, and the location is basically encoded using 2-bit indices, as you basically can see in this figure. Now moving on to the SSD slice architecture. So basically, the core compute unit is a 4x4 output stationary systolic array, where we enhance the traditional processing elements with sparse processing elements to support sparsity. And I'll introduce those in the, I'll explain the architecture of those in the next slide. Other features are that, typically matrix A supports dense or sparse data. The data get in from the A data, from global routing ports, the A data in, and get out from the A data out ports to be propagated and reused horizontally. However, vertically, basically, for the matrix B, which supports dense computation, the data are propagated and reused vertically, but we insert the data through the bit data global routing ports, but we propagate the data basically through the dedicated wires, bit det in and bit det out, as you can see in this figure. And this is very important because typically FPGAs have a columnar architecture, so we match this architecture to have significant routing savings. We have some input and output logic to maintain regularity in the design and make the downstream logic basically simpler. So we have some systolic data setup and some extraction logic. I'm not going to get into the details. You can find those in the paper. And we employ int8 and bfloat16 precisions, where accumulations is held in int32 and fp32 respectively. So now let's have a look on how the sparse processing elements look like. So in the dense mode, it's basically it operates as a regular dense processing element, which means that we have one multiple accumulate operation per cycle, and we have one pipeline register for both A and B data to basically forward the A and B values to the neighboring SPEs for data reuse, both horizontally and vertically, as you can see in this figure. Now, if we want to have a closer look on the 2/4 mode, the 2/4 sparsity mode. So basically, now things change a bit. We maintain matrix A, which is typically for weights, in the compressed format. And as you can see here, it has M by K divided by 2, because of the 2/4 sparsity, 50%. And we have M by K divided by 2 for both values and their indices. And we basically load 4 elements of matrix B in parallel. So we need 4 pipeline registers vertically. So we increase the ports by 4 and the reason is to basically attain acceleration from sparsity, because this is the intention, the scope of this work. And we also feed the 2-bit indices in the SPEs to basically because the 2-bit indices encode the position of the non-zero elements, are being used via multiplexer to basically select which A and B data need to get multiplied every clock cycle. And now, it gets a little bit tricky, but in order to maintain the systolic operation, we have to do some changes in the regular systolic array data flow. So basically, we need to load the B registers every 2 cycles, just because we have 2 elements every 4. We have a 2/4 sparsity mode, right? So we need to do 2 elements every time, and we need to, in order to have a functionally correct systolic operation, we need 2 pipeline registers for both the A values and their indices, as you can see in this figure. And what is interesting is that in this way, we can have a fully data reuse vertically and horizontally, because we propagate those values, both horizontally and vertically. And in this way, we can achieve 2x speed up over the dense case, as we can maintain exactly 1 Mach every clock cycle, similar to the dense operation. Now, for the 1 out of 4 and 1 out of 3 modes, basically for the 1 out of 4, we only need, again, we need 4 pipeline registers vertically, but we only need 1 pipeline register horizontally for A values and the indices, and we can have 4x speed up compared to the dense case. What is interesting for the 1 out of 3 mode, we basically do not need any additional hardware area, just because we are reusing the area for 2 out of 4 and 1 out of 4 by only using 3 out of every 4 ports and registers vertically. Now, moving on, let's have a brief overview of the gem implementation for the dense case, starting simply with the dense case, and see the difference between the sparse case. So basically, if we have X SSD slices horizontally and Y vertically, we can build Y times 4 times X times 4 systolic array size. And it's multiplied by 4, because remember, we have a 4 by 4 systolic array in the core of the SSD slice. Now, the matrices are typically stored in on-chip buffers. They are implemented using VRAMs in FPGAs, and they are partitioned into banks to basically fit with the correct bandwidth each SSD slice, as you can see in this figure. The data propagation, so we employ data reused by horizontally using the global routing resources. So basically, horizontally, you need to go to the global routing and connect to the next SSD slice, as you can see in this figure. But vertically, we use the dedicated wires. And notice that we only need to route only at the top edge of each SSD column of the B data. And of course, we also employ some control and tiling logic in the CLPs of the FPGAs to basically support any arbitrary gem size. Now, let's look at the difference with the sparse design. So for sparsity, first of all, the buffer A banks also need now to store the indices for the sparsity, the 2-bit indices. So we need a slightly higher bandwidth in the banks and wires to route in the FPGA, as you can see in this figure, for the 2-bit indices compared to the dense case. And for the B banks, basically, we need to route 4 of those B banks to basically feed each SSD column. And we need to do that due to the 4x increase in SSD slices ports in order to obtain the sparse acceleration I explained in the previous slides. But notice that this is basically amortized due to the dedicated wires, and this is why dedicated wires, in our case, the sparsity, are so important. And you need only to route basically the top edge of the 2D systolic array design, as you can see in this figure. Multiplexing logic is also utilized to efficiently reuse all those banks between sparsity modes. And you might need to do that just because you might want to support dynamic configuration of multiple or even all the sparse levels. And this is supported in the control logic, basically. And this is basically very important just because you might want to have a layer-wise sparsity, which means that in each layer of the deep learning workload has a different sparsity level, and you need to on the fly change from one sparsity level to another sparsity level, basically. And you need to make sure with some multiplexing logic or some other logic that you are effectively using all your banks and you don't leave any of the banks unused. Moving on to the FPGA architecture. So basically, we model an Agilex-like FPGA using coffee spice simulations. You can see here in this table the parameters of the FPGA architecture. We utilize a 7 nanometer FinFET A7 PDK, as you can see in this reference. We use a 20 kilobit VRAM model from the Stratix 10 values. The reason is because this is, again, this was used also by Andrew in his work at FPT 2023. And the reason is because basically this is a 40 nanometer Stratix. We do that because we don't, as far when I did the work, basically the Coffee didn't support 7 nanometer optimized VRAM model. So this is why we need to use, as Andrew did in his work, these Stratix 10NX values. I don't know if it's fixed now, but back then when I did the work, that was the case. We use an Agilex-like DSP, which used in reference for the Tensor slices from Aman Aurora, but we scaled down to 7 nanometer because this was a 22 nanometer work. And we found that basically we need to repeat the SSD slices every 15 FPGA columns, occupying only 40% of the total FPGA area, which is basically sufficient for deep learning workloads, as also found in Aman's work in reference 4. And you can see basically in purple color the SSD columns, and with other columns, the other colors, you can see the other FPGA resources. So we have CLBs, VRAMs, and DSP slices. Moving on to the implementation of the SSD slices. So we use Coffee's hybrid flow. In the standard cell flow, we use to implement the SSD core, which is basically an ASIC core. We employ the 7 nanometer A7 standard cell library using Synopsys and Cadence tool for placement and routing. For the routing interface to the FPGA, we use the Coffee Spice simulations. And now we basically take the SSD slices and remove all the Sparse features. We also remove the dedicated interconnects to build some slices which support only dense computation and are very similar to what Aman did with his Tensor slices. And we just call them STT-GIO slices from Systolic Tensor slices with global I/O interface or ports. And we do that basically. These slices act as our baseline for the comparison. And we find that in the total tile area, when we include both the core, the standard cell core, and also the routing interface, we see that we have less than 20% increase due to the sparsity features. And this is what we want to accurately quantify. How much more area do you need for sparsity? So moving on to the, we try to quantify the wire length, FPGA wire length gains of dedicated wires. Well, when we build gems across various systolic array sizes from 20 by 20 to 40 by 40, we can see that we have up to 31% less FPGA routing wire length due to the dedicated wires that we employed on SSDs. And this is for dense gems, just to have a fair comparison between SSD slices and STT-GIO slices, basically. And this shows how important it is to have dedicated interconnects column-wise, if you can, in an FPGA architecture. So moving on with sparse gem implementation, we first focus on the FPGA frequency. What is the maximum FPGA frequency we can obtain in gem designs going from 20 by 20 to 40 by 40 systolic array sizes? Well, we see that both SSD-based and STT-GIO-based have around 60 megahertz Fmax. And we see that we have basically only a 5% decrease when we increase the size from a 20 by 20 to 40 by 40 systolic array size. And when we implement the same sparse gems using traditional FPGA resources, so CLBs and DSPs mostly, we see that we have up to 5x less Fmax. And what's also interesting is that we can see that this Fmax decreases with the systolic array size, as we observed like around 50% drop from 20 by 20 to 40 by 40. And this shows that we can have enhanced Fmax scalability when using hardened slices for deep learning. Moving on to the FPGA area. So first of all, in the GEM implementation level, we observe again at less than 20% higher area for the sparse SSD-based gems compared to dense STD-GIO-based gems, which also aligns with the total tile area of the SSD slices. And when we compare those sparse gems with gems mapped to traditional FPGA resources, they show up to 11 times less area. And what's again also interesting is that when we increase the systolic array size from 20 by 20 to 40 by 40, we again observe the area difference to increase from 8x to 11x. So we can conclude that again, hardened slices significantly improve the area scalability in the FPGA. Going a step further, we want to basically quantify what is and estimate the deep learning speedup when using the SSD slices. So basically, we create an analytical model based on the GEM results that we have, and we compare the SSD slices for sparsity compared to STD-GIO slices for dense operation. We employ a layer-wise sparsity technique in reference 5, which uses neural architecture search to basically find the optimal sparsity level of each layer. And we see that we can achieve up to 3.5x speed up compared to the dense operation with only around 1% accuracy drop. And the DNN models here are VIT, so vision transformers, and CNNs, and basically those are DIT-B, DIT-S, and ConvNeXT-S, which all offer state-of-the-art performance in vision tasks. What is interesting is that we find that there's a different optimal sparsity solution for different deep learning workloads, and typically the bigger the model, the more sparsity you can extract out of it. So, for example, in DIT-B, you see that all layers can be 1 out of 4 and still have only 1% drop in accuracy. But for DIT small, because it's a smaller model, you might want for around or less than 1% sparsity, you might want to, you cannot go crazy and have 1 out of 4 sparsity. You can only have, let's say, 2 out of 4 sparsity. And for example, in ConvNeXT-S, we find that we might need all the sparsity levels, as you can see in this figure, to basically obtain the optimal sparsity, the optimal accuracy speed-up trade-off. So in conclusion, sparsity is inherent in modern deep learning workloads. Most deep learning accelerators support structured sparsity. For example, the NVIDIA GPUs. The FPGA architectures have been primarily optimized for AI, but they target dense deep learning workloads. So we propose in-fabric SSD slices, which basically support the most common sparsity levels, which are 2 out of 4, 1 out of 4, and the new sparsity level, which we call 1 out of 3. And our SSD-based sparse GEM accelerators offer substantial performance area and scalability compared to traditional FPGAs. And we show that deep learning workloads can attain up to 3.5x speed up when using SSD slices with minimal accuracy drop up to 1% when we compare to dense in-fabric acceleration. Yeah, thank you very much. And I'm happy to take any questions.